Okay, unit 1, whirlwind. I'm not even going to write it down because I'm going to need the space. All right, so where did we start? We started with the first chapter, which was all about experimentally how we determine the energy in a reaction. Okay, and there were 3, and you'll remember your chapter 9, 3 columns, because we cover 3 reactions or 3 different areas of the I don't even know what I'm saying anymore. It's been a long day. Okay, 3 formulas. And the first formula that we did was Q equals MC delta T. And the second formula we did is delta H equals N delta H. And the third formula we did was, well, we equaled them. Because if EP equals negative EK, then MC delta, oh, it's the other way actually, then N delta H equals MC delta T negative. So it was these 3 equations that we discussed, right? What was this equation? What was this all about?
Heat.
Heat. What else is it about? Energy. What kind of energy? Kinetic energy. Because all we were doing was warming something up or cooling something down. That's it. The M was the mass of that thing that we warmed or cooled up. The C was the specific heat capacity, or in other words, how good it is at insulating and conducting. It was a number that tells you about its power of insulation or the power of conducting. Not just it's a good conductor, it's a bad conductor, right? But actually this one is exactly 2.18 better of a conductor. And the delta T was a temperature change. And for this equation I talked about thermometer, thermometer, thermometer. Do you remember me saying that a million times? Why did I say that? Okay, temperature change is about the thermometer.
Might be like an indicator in the question.
Yeah, so if I see a thermometer and that indicates that it's a kinetic energy and I'm using this reaction.
The difference between the two is what you're using.
Students always mix up this mass. That mass is the mass of the thing that your thermometer is in. If my thermometer is in a solution, it's the mass of that solution. If my thermometer is the temperature change of the cup, it's the mass of the cup. Okay? Not the mass of the chunk of zinc I threw in there for the reaction to happen. Okay? So this was all about thermometer, thermometer, thermometer. The mass of the thermometer, the specific heat capacity of the thing that the thermometer, not the mass of the thermometer, the mass of the thing that the thermometer is in. So we did a whole bunch of styrofoam cup experiments here. We had a thermometer in our solution. I didn't care about the mass of that cup. I didn't care about the mass of zinc that I threw into that acid. I only cared about the volume of water because volume equals mass. And in water, the density is 1 gram per cubic centimeter. So if the volume is 1 milliliter, then the mass is 1 gram. Remember that? And I only care about the thermometer. So that was MC delta T. N delta H was not about this physical change, right? This was a physical change, where it's just warming up or cooling down. It's not about that. The N delta H equals N delta H is about not a physical change, but a chemical change. And so I'm looking at a chemical reaction. This is about a reaction. So now I do care about the zinc and the acid. I do care about that. Oh yeah, by the way, back to here. I said acid, and then I used volume and density of water.
Junior class change.
How am I able to do that? Acid, volume of water. Because it's a solution, and it's mostly water, so I can make the assumption that the specific heat capacity is the same as water, and that the volume and density is the same as water, right? Do you remember that? Okay, so acid, solution, or plain water, same thing. Okay? So this part is about the reaction, though, not just about it warming up, exothermic, endothermic, because of the... This is about the actual things that are reacting. So this is about the zinc and the HCl, making hydrogen gas and zinc chloride. This is about that. And how much energy I get from a reaction of this. And to balance it, I need a big 2 there. And what does delta H mean? Change in enthalpy. And it's common to mix up the 2 delta H's, right? Very common. So let's just when that happens, you should always do this, no matter what it is that you make a mix-up about. So these 2 delta H's here, what's the difference? What do we call this delta H? What is its name? I don't know, what am I asking for if I ask you for this delta H? You just told me. Yeah, enthalpy change. What else might I ask for if I'm looking for that delta H?
Total energy in reaction.
Energy. Often total, or they might not say total, but they're alluding to in this specific situation. Whereas the other delta H, this delta H, what's this delta H called? This is called enthalpy change or total energy. And for this situation, what's this delta H called? Molar enthalpy. Everybody okay with that? Molar enthalpy. So if I'm asking for molar enthalpy, I'm looking for this delta H. If I'm asking for energy, I'm looking for that delta H. What's the units of the first delta H? Units of that guy? Kilojoules. And units of this guy? Kilojoules per mole. Do you see I've got the units right beside each other. I've got the names right beside each other. This is very, very helpful because now you're totally comparing and contrasting 2 exact things. 2 exact things. Not just making a random list and making a random list. And then you still make the mistake on the question. Okay? What else? What else do we have on our list that we came up with the other day, Davin? Do you remember?
It was the analogy like the paycheck.
Okay, so this is equivalent to, if this is kilojoules per mole times moles, right? For number of moles, total energy. This is saying how much energy do I get in the reaction, the balanced chemical reaction. How many moles did I actually burn today? How much energy did I get today? Now today wasn't a big cooking day because I was at work all day, so my stove probably didn't, although the energy released per mole is the same each time, I'm not going to burn very many moles in my stove today. So my energy that I've had to use up in my house is going to be fairly small today. But Saturday is a big baking day, and this should be the same, shouldn't it? But this changes, because I'm going to make 5 batches of, I'm going to make some, actually I'm going to make some cupcakes for the volleyball team on Monday.
Really?
Yeah, really. Yeah. So here's my number of moles is changing. I'm making more stuff on Saturday. So that for the energy that I'm using up will be greater on Saturday. So this is your wage, how much I make per hour. This is how many hours I work. And therefore, at the end of the day, this is my paycheck. My paycheck constantly changes. Depending if it's a weekend, a summer month, constantly changes. But my hourly rate for that job should stay the same. Use your units. Use your units. Kilojoules per mole and the moles cancel out, leaving you with kilojoules. So kilojoules per mole has to be the one on the right. Molar enthalpy has to be on the right. Okay, so this is all, oh yeah, and then we did these equations where we had like, I'll just put the zinc and the hydrochloric acid again. let's say the delta H for this is, I don't know, negative, what does the negative mean? Negative delta H?
Losing energy.
Means it's exothermic. This thing is losing energy. So the delta H is, I don't know, let's just say 100 kilojoules for this reaction. How much is it per mole of HCl?
What's the double?
How much enthalpy change is per mole of HCl? I need to divide it by 2. Right now I have 2 moles of HCl, give me 100 kilojoules. So 1 mole of HCl will give me negative 50 kilojoules. Remember doing that? And of course, in that self, that's a half, and this is a half, and this is a 1, or half. Remember? Everybody okay? And it's about at this point where I think actually it was before this, where I started looking at enthalpy itself, and I was doing, do I have some space here? Yeah. And we talked about how delta H can be represented as negative for exo, positive for endo. Then we did these graphs where this axis was potential energy, and this axis is time, or as the reaction progresses. And if it's an exothermic energy level diagram, it looks like this. A and B give you C and D. Gabby, you should be frantically writing so that you're engaged in the material. And the delta H is negative.
This is an exothermic one, right?
And this is exothermic. Versus the endothermic diagram looked like this. Potential energy and time, and you have to put energy in to those chemicals. The delta H is positive because I'm putting energy into the chemicals, and A and B, let's make some different things up here. X and Y make Z and W. Do you remember doing that?
Yeah.
So if this shelf is higher than that shelf, it's endothermic. And we talked about these shelves and the potential energy also equating to stability. Do you remember that? And how the lower the shelf, the more stable. The lower the shelf, the more stable. And so as soon as you read a question about stability, you're thinking about this. These shapes, these graphs, this diagram. Okay? Stability equals these graphs. The higher the ball is on a shelf, the less stable it is. The more potential energy it has to fall. A ball on this shelf would have more stability, less potential to fall. It's the same thing. It's the same shelf, it's the same diagram. Okay? It's the same in physics as it is in chemistry. Remember that? And while we're on these graphs and on this topic, we should probably talk about activation energy. Do you remember what activation energy was? All these sticks and balls, like the ones on the ceiling here, all these sticks and balls have to be taken apart.
Energy required to take them.
And the energy that's required to take them apart then is the activation energy. So here's your activation energy. Up here, all your broken little bits and pieces all over the floor, ready to be put together again to form. Remember that? So EA, activation energy. And breaking bonds, right? Breaking all those A's and B's was, well look, endothermic. The shelf went up. Endothermic. And I had somebody come and try to break a marker to show putting energy into the bond, right? And James sprayed ink all over. Forming bonds is then exothermic. And every reaction involves breaking and forming bonds. They have to involve both. But if it's exothermic, then this must be greater than the endothermic, if it's overall exothermic. I must get more energy out from forming than I had to put in to break. So So the balance between these. So we have both of these exist in every chemical reaction, but one of these will be greater, and the one that is greater is whether the reaction is overall endo or overall exo. Okay? So breaking these molecules up, or Lego complexes, you're going to break up the Lego complex into all the little Lego bits on the floor now. That's took energy into the system, so there are all the particles all ready to go. And then you can put them together again, which is exothermic down. And the activation energy here would look a little like this, all the way from the shelf where they're made, those Lego pieces all together, break them apart, form. So this whole, from the shelf down up to the top of the crest of that, just like from that shelf to the crest of that, is activation energy. Okay? It looks different because I've got to kind of go past the delta H and keep going. They look different, but it's still from the first shelf to the top of the hill. You with me? And still, while we're on this graph, I'll talk about catalysts. So catalysts do what? What?
Speed up.
They speed up a reaction. How?
By lowering the activation.
By lowering the activation energy. Kind of. By providing an alternate path of a lower activation energy. So a new pathway, a new type of reaction. And that new type of reaction has less activation energy. But I still get the same products. And so because I can have more molecules now that have enough energy to do this, I now have a lower, more molecules can make it, so faster. So activation energy with a catalyst. Ugh. You with me? And then a taller hump would be the activation energy without a catalyst. And the analogy I gave there was about like Mount Everest. Only the fittest of the fit, only the molecules with the very, very most energy can make it up to the top of that crest. And I showed you an example of hydrogen peroxide. We were in Mr. Moore's lab for this one. And the hydrogen peroxide kind of does nothing. Maybe if you left it in your medicine cabinet for 10 years, then it would all decompose into oxygen in the water. But actually, not very much. Because only the fittest of the fit of those H2O2 molecules, only the ones with the most energy have enough energy to make it to the top of that activation energy crest, to the top of Mount Everest, to make it down to the Valley of Products. But if I came along to Mount Everest and I burrowed a tunnel, through to the other side, right? Just got halfway up the mountain and just started drilling right through. Now, not only can those really fit molecules go through, those really fit people go through, or the really high energy particles, but actually the ones that only have half the amount of energy, right? The people that are just kind of athletic can get to the other side too. So, more molecules have enough energy to make it over to the Valley of Products. And therefore it happens faster. And then you saw those bubbles, remember? In the soap. Happen instantly as soon as I added my catalyst. You saw loads and loads of bubbles. Okay, and that's because it held it, broke it up, made it go faster. So an alternate path of lower activation energy. Done. Done with catalysts? Oh yeah. Does the catalyst change the delta H? No. Does the catalyst change the levels of these potential energy stability? No. The only thing the catalyst does is changes the activation energy. That's it. Okay? And actually, if this really is time, I should maybe have this happen faster. It can change that a little bit there, right? That's okay. but not the level itself, not the number of energy itself. That is held within the bonds, and those bonds are still carbon attached to hydrogen, or whatever it is. So that bond hasn't changed. Everybody get it? Everybody happy? Okay. So that was a little bit of a sidetrack. Let's go back to this comparison table. So after we kind of mastered enthalpy and exactly what it means and the heat that's released and gained in our reactions and the molar enthalpy versus the total enthalpy, if this is about the reaction, this is about the zinc being dropped in the hydrochloric acid, and this is about how much hydrochloric acid we had in order to absorb that temperature change, we can have these two things equal. So every bit of energy that this reaction released went into my solution. And my thermometer read that. So according to the law of thermodynamics, this energy equaled that energy. This energy lost equaled this energy gained. Everybody there? So that's where we get this from then. The energy lost by this reaction is equal to the energy gained by that styrofoam cup. Why do we need the negative? Because one's lost, the other's gained. Are you a person that always forgets the negative, like me? Probably. So therefore, at the end of the day, you've got to think to yourself, what's my delta H answer? Because if it's exothermic, it better be negative, and if it's endothermic, it better be positive. And you just do that little double check to make sure that you're on the right track. Okay? Gab, you awake? Good. So these two things equal. The number of moles is not often given to you. It's normally mass over molar mass. Delta H is equal to negative mass C delta T. And this is the point where I lose students, because students that just, I have a formula, I can plug in numbers, I am a very good physicist, I'm a very good mathematician. You make awful chemists, because you can't understand that there's a difference between this mass and that mass. That this is the mass involved in the physical change, this is the mass involved in the reaction. And I am reacting zinc in my example that I've just given you. So this would be the mass of the zinc, but what's warming up is the solution. So this would be the mass of the solution, which is the HCl in this case, which is equal to water, because I can make the assumption that I have so very few H plus and Cl minuses compared to H2Os. So my density is equivalent. Within the significant figures, anyway. Okay? And people start to freak out, I don't know which mass goes where, I don't know which mass goes where, and you will make a mistake, and that's okay. And so, I think that's about it. We normally solve for this delta H, but you can, see, I forgot the negative. I always forget the negative. So when I'm done and I've solved for that delta H, I then ask myself, is my final answer exothermic or endothermic? Did the temperature go up? Exothermic? Okay, chuck in a negative at my final answer. Okay, because I am the type of person that I don't really care about the setup. I just get on with it, and then I make mistakes because I forgot the negative. So that's my coping mechanism, is just to check the theory behind it. If you're a type of person that methodically sets everything up before you begin, you're probably never going to forget that negative, and then you're fine. So we use this example here. I've just done a zinc and, right, the zinc mass in the styrofoam cup. But we often also use this example. So here's, we've done the zinc plus HCl. But here's another example that we could do where you've got a pot of water, remember this, over top of a variety of things. A candle, a stove, a camping stove, a methanol burner, a variety of things. Where you've got something reacting on the bottom, burning, and you're heating up something, a pot of water, and this is called a simple calorimeter. And the top bit is about your MC delta T, because that's the temperature change, and the bottom bit is about your reaction, and delta H, because that thing is reacting. Okay? And it's not about the whole candle, it's about the candle that burnt, the bit that burnt. So we have MC delta T and NH, and you are assuming that 100% of the energy goes into this calorimeter. That's a pretty rubbish assumption, right? That's a pretty rubbish assumption. A little bit better is that not only MC delta T of the water bit, but also the MC delta T of the can bit, because you know the can warms up, right? That's a little bit better. So the MC delta T of the water plus the MC delta T of the, I don't know, let's call it an aluminum camping pot. And here I would use the mass of the aluminum camping pot, the specific heat of the aluminum camping pot. It's going to warm up by the same temperature.
So do you only need one negative for your doing though?
Yeah,
Or do you
so
need-
that, I'm going to add that all up,
Right,
and then there's a negative in front of it.
okay.
Yep. That's a little bit better, because my heat didn't just go to the water, it went to the water and the can. The can warmed up, right? Whereas on this example I have a styrofoam cup. The styrofoam cup isn't really going to warm up. In fact, let's call it not warming up at all. So a 0 temperature change. If that number is 0 temperature change there, this whole term is equal to 0, so I can ignore it. So even though your C is in the data booklet, don't use it for styrofoam. Okay? The reason they put it in there is so that you're supposed to go, oh, look at this incredibly low C, or high, incredibly high C. It must be a very good insulator. You don't know that styrofoam cups aren't good insulators? You guys live in a hockey world. You know that styrofoam cups are good insulators, right? So, if that's a styrofoam cup, you're not going to use that. If it's an aluminum can, here's the tricky part, the game we have to play. If they tell you it's aluminum, if they tell you it's mass, then we use it. If they don't tell you, then we don't use it.
It's only if they give you a match.
Only if they give you the information, then you use it. It's a little ambiguous. I don't like it. I wish they said, please include the container in your calculations. And then, because you're testing students on their test-taking skills all of a sudden, and that's not right. But it is what it is, and we play the game. Okay, so if they give you the mass of aluminum, if they tell you it's aluminum, so you can find the specific heat capacity in your data booklet, then you can do that. If they don't give it to you, you can't do it. You with me? Okay. So, but even better than this basic calorimeter, if this is just a candle and I am just warming up a pot of water and I'm trying to find the delta H of this candle, of the reaction of this candle, the burning of that candle, it's not precise enough for the reaction of a Mars bar. If I put a Mars bar and I make a package of Mars bar, I need to know exactly how many calories are going to be given out if a person eats that Mars bar and burns that Mars bar in their cellular respiration in their cells. Because that's a combustion, right? The glucose in the Mars bar plus the oxygen, that's combustion. So if I'm putting a number on that Mars bar, I can't do it this way. Burn a Mars bar, have some water heated up, figure out the temperature change of the water, and equate that to the delta H of the Mars bar. I will get sued. It's not precise enough. So to be more precise, I have to take the same concept, but I'm going to use what's even more precise than this? Bomb calorimeter. So a simple calorimeter and a bomb calorimeter.
It's not like this.
That's the big C delta T. That's right. So in this case, we have N delta H equals big C delta T. And if you're the type of person that keeps getting these big C's and little c's mixed up, if you've always buried your head in the sand and hope this will never go away, it won't. So make yourself a comparison table about big C's and little c's. So the big C, the little c, and the big C. What's the little c called? Specific heat capacity. What's the big C called?
Heat capacity.
Just heat capacity. What is big C? Not average.
The total, like.
Total. All the masses of the water, the cup, the thermometer, the stirrer, the styrofoam container around it all those masses, all added up, all those specific heat capacities multiplied by the masses, all added up, done. Because I'm using the same instrument each time, I only have to do it once. And I can chuck my Mars bar in there and my lettuce of leaf, my whatever that's called, leaf of lettuce in there. Okay, because it's the same system. So my big C is the same for the same instrument. So it's all heat lost calculated for. And little c is one specific, that's why it's specific heat capacity, one thing, just water, just aluminum. So all heat loss. Sorry, my son scratched my nose the other day, and it literally like a big scratch across my nose. It just keeps bleeding. Right, all heat loss is calculated for. That's okay. And then little c is just one thing. It's all right as long as you're healthy for playoffs on Monday. Sorry.
Yeah. Bethan's back to school today.
I saw that. Okay. Happy? Oh yeah, units. What are the units for little c?
Kilojoules per mole.
Kilojoules
Degrees Celsius.
per gram degrees Celsius. And big C is just kilojoules per degrees Celsius. The grams are
The
gone.
degrees Celsius is always on the bottom.
Degrees Celsius are on the bottom. Because I have to cancel out the C the temperature you're multiplying it by. Okay, so how do you know it's a bomb calorimeter? Well, if it says bomb calorimeter, the following was done in a bomb calorimeter. If they give you the units that look like that instead of like that, if they say heat capacity instead of specific heat capacity, now you know to use big C. Or, hey, guess what? If you can't find the mass of the thing that's warming up, because there's no MC delta T here anymore. So if you can't find an M of a solution or the hydrochloric acid or don't just start using the mass of the candle or the Mars bar or whatever. Okay, that is the first chapter. Chapter 9 in your textbook. Questions on that? No. Okay, ready for chapter 10 then? Oh, and this is 11, so we've done 2 chapters there, that's good. Okay. Let me just erase the board. Okay, so that was all about, may I borrow a tissue? That was all about experiments, right? What an exciting way to start. The chemistry, it's all about experiments. MC delta T, all about experiments. The calorimeter, all about experiments. Gabby? I'm not going over this again in a period 1. You need to be paying attention now. Sigh all you like. Right. The second chapter is about how do we calculate delta H, not experimentally, but theoretically. Because I can't burn everything as much as you might like to. You can go if you want to. Okay.
Really, everyone talks. Oh, okay.
Graham, pay attention.
Immediately.
All right. But see, Graham's actually listening. I can tell. He's nodding his head. He's writing things down. He's playing along.
Proof. The defense rests. I have a.
Did you see how much stuff I had? Okay.
I have small writing.
Theoretically. So there are 2 ways we can theoretically calculate delta H. What are they? Theoretically. So we can't burn everything. Not everything can go in a calorimeter. Especially like, let's say we were going to make that candle, the formation of that candle. Carbon and hydrogen and oxygen. You think that when you magically just throw those things in a container, you magically get wax?
Yes.
A candle? Doesn't happen. So if I want to know the formation for enthalpy of that paraffin wax, I got to do it a special way, a different way. Okay? Because I can chuck zinc in an acid and I get bubbles and everything's great. But I can't chuck carbon and hydrogen and oxygen together and get a candle. It doesn't work out that way. So if I want to know the delta H4, I can't remember what it is, but let's say C3234H. In fact, it doesn't have oxygen in it. Paraffin. I don't know. 20. No, it'd be more, wouldn't it? So 52. I don't know. Making it up. But something like that, right? Those things don't get thrown together. So I've got to come up with two theoretical ways. One is algebraically, and the other one is called Hess's law of formations, or something like that. And it's all Hess's law, by the way. So Hess's law says if I can't do it directly in a calorimeter, I can do it indirectly. And here's two ways of doing things indirectly. The first way that we learned is algebraically. And that's the whole flip, multiply, and add. Flip, multiply, and add. So, oh, I went off my board. See where I rubbed it out. Bad news bear. Okay. Flip, multiply, and add. So you look for your star pupil. Do you remember doing that? Remember? So these are really hard to make up, but I'll do the best I can, okay? If I am asked to find what is the enthalpy change for, by the way, just while I'm thinking about it, the other thing that we covered in chapter 9 was we looked at how you can communicate enthalpy change. 1, the reaction. 2, reaction space, delta H equals negative or positive number. And then the third way was taking that negative or positive number and putting it into the reaction. Do you remember that? If it's negative, it goes as a product. If it's positive, it goes as a reactant. Remember that? Okay, so that was chapter 9. Okay, back to this. So what is the enthalpy change? Oh, my writing's atrocious today. For something like this. I don't know. Blah, 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 blah. NH3 plus HCl goes to NH4Cl. Okay? I wanted kind of something with a big number. Let's go H2SO4. And then let's make this this one. I'll need 2 of those. Okay. Okay. So they give you a whole bunch of equations, and you have to either flip them, multiply them, and then at the very end we add them. So the first equation they give you is something like this. N2 and H2 make NH3, and the delta H for this is, totally making these numbers up, let's just go within the 150 kilojoules. And of course this is 2 of these and 3 of these. Everybody okay so far? So this is the first equation they give you. And you look at this equation and you think to yourself, what is my star pupil? Nitrogen, I don't care about nitrogen. Hydrogen, I don't care about hydrogen. Or maybe hydrogen's in loads of places. I might care about it, but it's in loads of places. So it's not my star pupil. This is my star pupil because A, it's in my destination, and B, it's in neither of the other equations, which I haven't written yet. Okay? So I look at this and I think, oh, this is the star pupil. The thing I need to do with this equation, though, is I need to flip it because, right, it needs to be reactant in my destination. Here it's a product, that's a problem. So I rewrite this equation to say 2 NH3s go to an N2 and 3 H2s. And when I flip this, I flip the sign of my delta H. So that's what I mean by flipping. Okay, so this is the next reaction that you come across, is this one. 2 H2SO4s and 4 NaOHs give you 2, forgot about that little 2 there. That's okay. 2 Na2SO4s and 4 waters. And the delta H for this is negative 820. Remember, all neutralizations are negative. Most formations are negative. Okay. All right, who's my star pupil here? H2SO4. Do I need to flip it?
No.
Do I need to multiply it or divide it?
Divide.
I need to divide it by 2 because I only want 1, and here I have 2. So I'm going to divide it by 2, divide that by 2, divide that by 2. Oops. Divide that by 2. And what do I have to do to my delta H? Divide it by 2, negative 410. What am I hoping about these NH4s? Of this thing that I'm pointing at, sodium hydroxides. I'm hoping that they will cancel out eventually.
Shannon's at the door looking for something.
What?
Oh. Yes?
Melissa? Yeah, she's at the back.
Oh,
Yeah, Melissa. Okay, and then when you're all done, the flipping and multiplying, everything should cancel out that you want to cancel out. You should be only left with that, and you add your delta H's, and the delta H that you end up with is the delta H of the reaction that you end up with. Can we just leave it at that?
Yes.
Okay, good. Moving
I
on.
have no.
Pass's law of formation. Is this lovely? Those of us that like math
Love it.
get a good kick out of these. Delta H naught for the reaction, so the thing you're looking at, is equal to the sum, ooh, that's a crazy sum, of the number of moles of the formation enthalpies of your products minus the sum of the number of moles times the enthalpy of formation of the reactants. Where do I find these? In your data booklet. And so, what did I have? NH3 plus H2SO4 went to
NH4,
NH4, 2SO4s.
You added 2 in front of that.
Okay. So for this chemical reaction, in order to do it this way, first of all, they wouldn't give you anything to flip or multiply. Okay? Or sometimes they would say, solve using Hess's law of the enthalpy of formations. The sum of the enthalpy of formations. I forgot to put the word sum in there, but anyway. Okay, so you look all these up in your data booklet, you look up the product, that's this one, and you find the sum of that number there, minus some more brackets. 2 ammonias. So 2 times whatever you look up in the data booklet for ammonia, plus, because it's the sum of, so plus 1 sulfuric acid. 1 times whatever sulfuric acid is in your data booklet. And tappity tap tap in your calculator and you get some kind of delta H. Let's say this is negative 800. Now sometimes they give you, as I did in your unit test, I gave you the delta H of this reaction, but I asked you for formation of whatever. So now it's some fancy algebra. Negative 800 equals W minus 2 times, I don't know, negative 100 plus 1 times negative 250. And you have to solve for W. Do you remember? And it's just, once you've set it up, it's just fancy algebra. Tap that in your calculator so it into just one number. Now I have number equals unknown minus a number. That's simple. Okay, but when it's all like this, it doesn't look very simple. So start to condense it. Shove your numbers together wherever you can. And this minus is on the outside of this bracket. So you're going to do all this stuff first, and then subtract that. I think that's it. I think that's it. Okay, so the package I just gave you has some questions, which will help you kind of come to terms with all that stuff. So the midterm is on that, and it's on the unit exam you just wrote. Simple, right?
It was on nothing. It wasn't on.